All right, so today we continue on to the next part of x86. Last week we talked about compute operation. Last week we talked about if else, how to support jump and branch, right? The next part of the class will evolve around loops. How do we repeat things? So a quick recap on the jump instruction, right? It's as simple as you jump to certain destination. Destinations are the line of code that you want to jump to, which is some address in the memory, because your program is in the memory, right? And for a loop, where do you jump to? Yeah, back to the first line of your loop, right? And as simple as that. Basically, here's what you have to do for the loop instruction. You go through the body of your loop. At the end, you check the condition, jump back to the beginning if needed. Otherwise, you go through the next line, which exits the loop. So that's kind of like the overall goal that you have to do, right? Think of it as a go-to command in C, despite the fact that I would discourage anyone to use the go-to command because it actually brings in weird side effects if your program is complicated. Now we talked about conditional move from last week as well. That I said these convert if else into a straight line code, and you can use it to implement a simple if else. Yes.
So I know we probably already told, but what was the difference between
It's the equivalent. Jump is used in assembly. Go to is used in C.
well,
Yeah. Go to, you can go to this line. It basically will run your code and go to that line. Which is kind of weird. If that line is in a different function, you think about it. That's why you don't use go to in C. It's not that safe.
what if you did jump to a different function with
Well, in assembly, function calls handled in a different way. So by default, everything in assembly is dangerous. So you kind of have to know where you're jumping to by default. We also talk about don't use conditional move if your if else is huge, because you have to do both the if part and the else part. And then for today, we will use population count as the motivation example for our loop. Population count means that I have an input and I want to count how many, if I convert my input into a binary number, how many of the ones are there. For example, if the input is 3, top count of 3 should be 2 because it's 1, 1. If my input is 7, 7 in binary is 1, 1, 1, right? So population count of 7 is 3. Top count of 12, 12 is 1, 1, 0, 0. Top count of 12 is 2 because there's 2 ones in my binary representation of the number 12, right? And that's it. That's my logic, right? I can implement this using a loop where I have a result that accumulates every time I see the ones at the end. So I'll just check is 1 at the end of my number in binary format. If yes, count up. If no, stay the same. Shift everything to the right by 1 and keep doing this all the time until everything is 0, until my input becomes 0, basically. So that's my logic. Result will be incremented by 1 if the last bit of x is 1. I can do this quickly by AND x with 1. If I AND x with 1, I just take the last bit, right? Because anything AND with 1 is that thing. So if the last bit is 0, this becomes 0. If the last bit is 1, this becomes 1. Then I add result to it. Afterward, I shift x by 1. This is basically x equal x shift right and y, or not shift left, my bad. X equal shift x shift right by 1. I push 1 bit over, basically, to check the next bit, until while x means that I'm going to keep doing this until x becomes 0. Until x becomes 0. If x becomes 0, while 0 is a false, so you go out of the loop, you return results. The easiest way you can convert to assembly is implement this logic using go to in C first. So instead of a while loop in here it's like do while, right? You change that to I use go to by doing this. That's my loop body, right? This is the same loop. Then at the end, I check if x is 0 or not. If it's 0, go to loop, and I define loop here. In C language, you can label the line. This is basically labeling. I do name followed by colon, means that I will label this line with that name. So over here, I label that line with the name loop. Then you can use go to loop, go to some label. To go to that line, you just label. So over here, if x is non-zero, you go back to the loop and you keep doing this until x is 0 and you go out of the loop. Any question about the C implementation here? All right. So now that you have the go-to version implemented, here is how you can do this in assembly. Let's first assume that the argument x has been being put in RDI. Let's assume that x is in RDI. Let's also assume that the result, when you return result, the result has to be in RAX. Right? So these are the two assumptions so far. X has to be in RDI and results has to be in RAX at the end. Okay. How do I implement assembly from this? The first thing I do is what? What's the first line here? Result equals 0, right? Result equals 0. So I just do put 0 into AX. This is like result equals 0.
What's the unsigned of x?
That's the input. That the function name is p count go to, and I don't have the whole line, so that goes to the next line. Yeah. So that's the input x, variable name x is unsigned long. Now the next line here, I label loop, right? So in assembly, you see the same thing. But when you compile your code, usually the label turns into just a number. Over here, it just by chance, it turns to .l2. Basically means the label name is .l2. If you want to go back to this line, you can always do jump .l2. It would jump back to here. Okay. Now, what's the next thing? The next thing is I know that RDI is the argument x, right? And you need to know x and 1, and you add the result into the sum. You add the result of the AND into the sum. So the first thing you do is, this is x, right? This is temp, basically this is temp equal x. Now the next line is temp equal temp and 1. I move x into some temp register and I AND that guy with 1. So these two lines, this is step 1, right? Step 1 corresponds to this line. These two lines are step 2. Step 2 corresponds to just this box here. This box here, this box I do here. I do x and 1. Now, the next thing is, this is step 3. That's the next line. Whatever the result I got, I add that to my result variable. Then this is step 4, which corresponds to this line. Now, when you do the shifting, right, with the status register, the shifting, if it results in 0 after the shift, what would happen? If I shift and the result is 0, it will set the 0 flag to be 1. Remember in x86, if you do something, you always update the status bit. In this case, you're shifting, and if the shift results in a 0, you will have the 0 flag set to be 1. So in that case, the flag is set, right? So you can do just jump not equal. Jump not equal would look at the 0 flag. If it's a 1, you don't jump. If it's a 0, you jump. This is step 5, which corresponds to this line. So if the result of the shift is a 0, you don't jump. Jump not equal, all right? Jump not equal. Jump not equal to 0. If it's not equal to 0, you jump back. If it's equal to 0, you go down. The next line is return. This is step 6. So that's when you return the value out of the function call. All right. Any questions so far?
So what is the double arrow equal to?
Double arrow equal. Okay. So the question is, what is this, right? This is the same as x equal x shift right by 1. Yes. Oh, yeah. So EDX and RDX, actually, they are the same guy. RDX is 8 bytes long. EDX is 4 bytes long, but it points to the same register. Think of it as a temp. You have long temp, a temp, which is a long format, which is 8 byte format. That's RDX. EDX is as if you cast that guy into int temp, but it's still the same temp variable, same guy.
You can make the byte short.
You originally you have 8 bytes. When you say EDX, you only take the last 4 bytes from it. Why is that okay? Because the compiler sees the and with the 1, right? And with 1 guarantee that whatever you have right now, you're just gonna have one bit left at the end. So it's totally safe to just cast from RDX to EDX because the top bit doesn't matter. It will get and with 0 anyway, so it will all be gone.
So you can store it as short, and you can read it as RDX.
Yes, basically the same thing. You can use it as the R variant, which would take the entire 8 bytes, or you can use it as the E variant, which is 4 bytes. Then there's also the just AX, which is 2 bytes, and then AL, which is only 1 byte, the last byte. Not in this case DX and DL, because it's RDX, EDX, DX, and DL. Yes. Yes, because this is more, to be honest, it's more efficient to just stream 4 bytes rather than stream 8 bytes, basically in that one.
Will the value change if you make it from RDX to EDX?
Yes, if the top bit has value in them, right? But in this case, the next operation is an AND operation, and you know that you are ANDing with 1. So in this case, even with DL is okay because you know that the top bit is gone after this operation anyway.
So about the shifting, what does it do when shifting? Where does it shift the thing?
Oh, okay. You mean what happened when you shift things, right? So let's say you have the number 7, 1, 1, 1, and you shift to the right by 1. What happened is everything gets pushed to the right. If it fall off the cliff, get rid of it. So this becomes 1, 1. So 7 shift right by 1 is 3. And this is basically what we need, right? Because we want to count the number 1. So we,
by 1 byte.
Yeah, we just check the last bit, shift, check the last bit afterward, shift, check the last bit afterward, shift until everything is 0. All right, any other questions? So that's a do while, right? In general, let's say you write any program and you have a do while loop, and you have to convert that to assembly. Recommend strategy, build the go-to version from your C code. So it becomes like a loop marking, like some name, the body of the loop. If else, if that thing is true, go back to the body of the loop. That's it. That's how you can convert do while loop into the go-to version. And the body is basically your loop body. All right. The body is basically your loop body, whatever goes in your loop. Now, the while loop is a little bit different from do while in what way? Do while always do the first iteration, then you check. While loop, you check first, right? So if you want to do the go-to version of this guy, right? The while loop. So the first thing you have to do is not the first iteration. The first thing you have to do is check first. Check first. So the easiest way you can implement this is using the what we call jump to the middle technique, which means literally jump to the first thing you do, jump to the logic that tests the condition. So you go to the logic that do the if else to check the condition. If true, then go to your loop body. If false, you fall down and finish the loop. Basically, if you look at how the execution of your code go, right? Let me change a different ink color here. You start from here, right? You jump here, then you keep going in this loop until it's done, then you exit the loop. The reason why we call jump to the middle is the loop body is in the middle here. Then the first thing you do is you break this flow, you jump to the middle of your loop body to do the tech checking first. That's why the technique is called jump to the middle, right?
What line would you have in the loop body which goes and checks the test again to go in the while loop?
Yeah, so here's an example. Let's do pop count using the while loop, right? So you do while x, if x is non-zero, you do population count. The same thing as the do while. Basically, it just switch to while loop. The first thing you do is go to test, right? The first thing you do is jump here. But you will imagine this is your loop body, right? Well, with the condition check, sorry about that, I mentioned Thai word. The loop body with the condition check, all right? So the first thing you do is to jump in the middle. First, go to the condition check. If it's true, then you go back to the loop body and then go down to condition check, go back to the loop body, go to condition check, and you're done. All right. Any questions so far? With this, replace go to with jump and you're done. Okay. Every time you see go to, replace that with jump and then you're done. So over here, you can convert while loop to the do while, right? Instead of doing jump to the middle, one thing you can do is condition check, then here's the loop. So this is alternative to jump to the middle. So if you don't want to jump to the middle to do the condition check, the first thing you do is, well, it's a while loop. The first thing is check the condition. If it's false, finish your thing. Skip the loop. So the go-to version is condition check. This is loop body. If condition check in the beginning is false, you skip this entire thing, go to done. So you never jump to the middle of your loop body. You never jump to the middle of your loop body. If the first condition check is false, you skip the whole loop. Then if it's true, the loop body stay intact. There's no entry in the middle. How many people are now confused by why is this so important? Why do you have to have two techniques? If you start to go into a more advanced topic in compiler, like how do you build GCC? It just happened that entry into the middle of your loop body is really hard to optimize. It's just much easier to optimize your code if you skip the loop body entirely and there's no side entrance, we call it side entrance. into this block of loop body. So if you don't do the side entrance, you do the condition check and skip the whole thing, your code is likely faster. Your code is likely faster. It has to do with what has to be alive when you enter into the loop body and what are the additional conditions that have to check and make sure things are true when you optimize your code in the compiler. So for now, just first of all, realize that there are multiple ways you can implement the while loop. And this way, the alternative doesn't have the side entrance into your loop body. You just either skip the loop or do the loop. All right?
What is the, go back?
Yeah.
What is the use with item?
Oh, okay, okay.
What-
Yeah, this is a great question. So here you see O1 and OG, right? So OG is the optimization flag that will allow you to debug a little bit easier. This is like will behave the same way as the way you intend your code to be. So your assembly is gonna look like jump to the middle version because your while loop fundamentally is jump to the middle. O1 is the optimization flag. So there are multiple level optimization with GCC. You can do O0. O0 means that I don't optimize anything. O1, yes?
Does the default one be used when you just
Depending on the version, actually, but I think the default is always O0 for most version of GCC. But I've seen sometimes it try to still optimize something, right? Then O1 is I will enable the subset of optimization that are known to like I would say graduate level compiler class. Then there's O2 and then O3. O2 is I will apply optimization known to me that is also has been checked and tested that they're safe, guaranteed that they're safe. O3 is everything known to planet Earth that I can apply, but some of these might have side effects that are not safe. So O3 is safe for the most part. O2 is really fast and really safe. What then? If you're wondering, then why don't we just do O2 all the time, right? It make your compiler taking a much longer time to compile your code. So if you work at a company, sometimes when you compile a code and do some test run, there are times when I have to wait like 15 minutes to compile. So if I do O2 and that 15 minutes turns into 35 minutes, it means that if I want to debug something simple, I have to wait 35 minutes to see the effects. So I would rather just use simple optimization so I can quickly test my code and move on with my bug. Then for the production version, I use O2 and O3 afterwards. That's okay. All right. So yeah, if you do -O1, the compiler would perform this optimization for the case whenever it see the while loop. Whenever it see the while loop, it do the checking first, skip the entire loop. So that allows no side entrance into your loop body. And that is fast. That is faster, basically. This may basically make your code run faster. All right. So now that you have the while loop, you can do the second version where you first check, right? If not x, if x is not, if x is 0, what happens? You go to done. If x becomes 0, not x is going to be true, right? If this is true, you jump here. If x is 0, you jump there. Then this is loop body.
how does the loop exactly work in this case? Because X is the unsigned binary number.
X is your input. Again, x your input.
X is the input.
Yeah. It's input to the function that you want to do population count, right? It's like the number you want to count how many ones are in my binary representation of x.
So when does it stop? Like
when x becomes 0. Because you shift, you basically This line, right? This line guarantee that you're gonna shift x to the right by 1 every iteration. Eventually, you're gonna put all those 1 off the cliff and become 0. Right? Any question about the while loop? Again, the only key difference, check first, then you go to loop body. That's it. Simple. Now, to write assembly code, again, go to its jump. So when you check for x, basically you load x and check if x is 0. If it's 0, go to done. If not, go to loop. Jump to loop, basically, jump to loop. Inside the loop body, the same assembly apply. Then you do jump not equal to loop. Now, the last form, which is actually the most often used, I guess, is the for loop. The for loop has 4 parts, basically: initialization, testing, update, and the loop body, right? And if you think about it, the update is like at the end of the loop body, because it's always like body update, body update. The sequence is in it, right? Loop body, update, and then you do the testing here. Init, test, loop body, update. And if once you update, you go back to test. If the test is false, you go to done, right? This is the same as you do init with a while loop, right? I mean, it's the same thing. You initialize the rest of your while loop, and the update is at the end of your while loop. Which also means that I can convert this to a do while to prevent the entry to the middle. Again, the problem is I don't want to do jump to the middle. I want to jump at the end. So I can convert the while loop to a do while version that doesn't jump to the middle. So here is the conversion, the first conversion to the while loop, right? Init, test, body, update, right? Which means that you have, again, init, test, and update. Okay, do body is just shifting and writing the results, right? So I can write it this way: result equals 0, because initialization is for I equals 0. I is less than the size of your data size, I plus plus, right? The first line is I equals 0. While I is less than W size is the size of X, how many bits are in X. Then this is the loop body. And this is the update. Okay. Huh? What results? You mean what is the result here? Yeah. Yeah, this program basically and every single it check and check how many is 1. How many of them are 1, basically. Yeah. Now you can then change that while loop, which is now in a do while loop, into the go-to version. The go-to version is basically here, init, right? Then you check, you first check. If it's not true, you jump to done. If it's true, you go to the loop body here, which also has the update and the check at the end. Now it looks like a do while loop. The first iteration you check before you enter the loop. Then you keep doing the loop until you're done, then you exit. Yes. Huh? Oh, in here, basically the implementation for the for loop, we would, instead of shifting until x becomes 0, we shift x until we know the size of x is long integer, right? So in this case, you just need, you know that you have to shift only 64 times. So in this case, the W size is going to be 64. It's like a constant to the size of the integer x. So in this case, W size is going to be mapped somewhere to 64. All right, so over here, you might see a few optimizations that for sure the compiler will do. Here's one thing. What's I in the beginning is going to be 0, right? And W size, as I said, is going to be 64. So this basically becomes if 0 is less than 64, right? Basically, that becomes 0 is less than 64. One of the technique that GCC apply for sure is what we call constant propagation. Constant propagation means that I see I is less than W size. At that point, I'll check, do I know I? Do I know what is the value of I? Because if I know the value of I know what this, is this true or is this false? Ahead of time. When I compile my code, I know for sure I is what? 0, right? And I know for sure W size is 64. So what compiler would do, GCC would replace I with 0, replace W size with 64, perform the evaluation, and get rid of that if, because it's going to be true. 0 is going to be less than 64, so you must do the loop. So, for the C code here, when you compile with the compiler, you might not spot this guy. It will be gone. It will be gone from your assembly because the compiler detects that, hey, you don't have to even run that line. It performs some optimization to get rid of that for you, basically. So when you compile your code with this exact code, you might not see the assembly code that corresponds to that 2 lines. It's gone. All right. Yeah.
After it finishes the second test, it goes into the loop. And does it go through the test again? No.
It goes into the loop.
Yeah, and after the loop, it takes the test again.
Yeah, that's always test at the end. You see, they have to test at the end, right? It's just the first test, right? It's just the first test. Compiler would detect that, hey, you don't even have to do that because it's always going to be going into the loop. All right, so any question about loop implementation? So you can always, now you have go to, right? Every time you see go to, think, jump, the label like loop or test change to .l2, .l3, basically like assembly would have the name. You can also still use .loop. If you write assembly on your own, you can write whatever names you want, but when you compile your code, they'll just do .l with some number. It's like automatically assigned, so they know where to jump to. All right. Any question? Yes. Uh-huh. Oh, that's a great question. So your question basically boils down to for loop seems more complicated. So why is it performing as well as a while loop, right? So the compiler basically would, I mean, when you look at the whole operation you have to do, right? The only addition is you have the initialization. That's the only difference, right? The initialization. The update, the while loop, you have to do it anyway, the update. All right. So if you think about the total amount of operations you have to do, it's the same. It's the same. That's why it performs the same way. But in terms of the tools that the language are giving you, the for loop is a little bit easier to program because the thing that has to do with the update of each iteration is happening inside just one parenthesis at the beginning. And whatever go to your loop body, it's just the loop body alone. You don't have to worry about the update. You don't have to worry about the testing. You don't have to worry about initialization. It's kind of like a feature of the language rather than the features of the like the in terms of performance optimization. So you still run the same amount of, you have to do the same amount of work anyway in the while loop. Is it clear now? Yeah, okay. Yeah. Basically the work is the same. It's just a little bit easier to write the code for. All right, so now the next topic, right, is a quick summary on control instruction. Because we covered if else from last week, the jump, right? Then we have the do while, the while loop. We have conditional jump, conditional move, indirect jump. This is basically what we are going to go to next.
What is the assembly language
Yeah.
for infinite? For
Okay.
while?
Great question. It doesn't check.
So it is one thing.
So here's what I would classify the compiler as, right? Infinite loop is whose fault? The programmer, the compiler, the language, or the hardware? It's the user fault, it's the programmer fault. And the thing is, the compiler would compile the code in the exact way that the programmer tells the computer to do. And in that case, just happened the programmer tells the computer to go into the infinite loop. So in that case, the compiler would just follow the command. Say, hey, okay, I will keep doing infinite loop.
Is there like cases, like there's no like a safety case, like a syntax error or like that?
Well, I mean, you can use check, yes, in some cases, but like, let me give one example, right? Can you always connect to Steam client any time of the day? It basically means that the server will keep accepting any new connection, right? So the server side, you have an infinite loop that wrap up. I will keep listening to new connections. So it's a while loop that never finish. So in that way, right, from the compiler point of view, how can you detect that this is a legit infinite loop that the programmer really wanted to have, or a bug from some incident that caused an infinite loop? It's impossible, right? It's more like the intention of the programmer. So yes, I guess you can write the tool to try to detect infinite loop. But again, the compiler will not prevent you from compiling that, because sometimes it's actually something you want to do. It might give you warning, for example, right? So yeah, hopefully that answer. Those are like, yeah. So today, like the question is really interesting. This is good. All right, so we cover jump to the middle, we cover do while, we're gonna now cover indirect jump. Indirect jump has to do with switch case. How many of you use switch case already on your code? Good. Now let me talk about how switch case works, right? So switch case is, imagine you have to do like 5 nested if else, because you're having like, for each input you have different conditions that you have to perform. The body of the if else is going to be looking different. So you can have if else, if else, if else, if else, if else, if else, and else, which is kind of annoying. You don't want to write that many if else cases, right? Switch case is an answer to that. And the way it works is it starts with the term switch. That's a keyword that says, whatever going here, I want to check the value of that number. It can be a variable, it can be anything. It's an input to the switch argument. Then you follow by a bunch of cases. The case will have the number tied to that. For example, you see case 1. It means that if x is 1, if x is 1, do this. If x is 2, do this. If x is 3, do this. If x is, in this case, 5 or 6, because it's case 5 and case 6, they share the same case, do this. Default means that if x doesn't match any of the value you've seen so far, do this. And now here's a special thing of switch case on top of just a long string of if else. One more special thing, you see this break keyword, right? Whenever you see the break keyword, you finish the switch case. You finish from that line, you exit the whole block. Huh?
It's like a go to done.
Yeah, think of it that way. Yes, it's like go to done. Basically, when you see the word break, you look at what is the block that cover what I'm doing right now, and you go out of it. Now, you can see that for most cases, you have to break at the end, right? That's normal. That's actually a common thing to do. Now, you see how case 2 doesn't have to break. And I have a comment that says fall through. So that's a special case where if I don't put the break in, when x is 2, you first do w equal y divided by c, then you go to the next line, which is w equals w plus c before you break. That's why we call it fall through. It's actually falling through that next case as well. All right. Any questions so far? Yes. Uh-huh. Exactly. It start with that first line in case 2, and then it would take part in whatever case 3 has to do. Keep going, and then only stop when you see the break. Yes.
I remember you saying like if else and predicts, it calculates else and it calculates both, right? Do that for this also.
Great question. So one of the things that your CPU loves to do is there's the logic called branch prediction that try to predict, are you going into the if or are you going into the else? Over here, yes, it also try to predict where you're going. Internally in the hardware, there are also proposals to kind of like do this in a compiler and tag like a probability of like there's a 90% probability going here and things like that as well. But these are like advanced topics. Basically, they attempt to predict how often you go here, so you try to run a line 8 of 9.
What happens after it goes through? Does it take for case 3 or?
It doesn't check for case 3. If x is 2, you run the first line of case 2, then you fall through, run the first line of case 3. Fall through means literally going through the next case. Yeah. So now we will talk about indirect jump, which is the assembly answer to how to implement this thing. Because you can imagine, obviously, one thing you can do, a bunch of jumps, right? Check for x, jump here, jump here, jump here, jump here, jump here, which is kind of annoying to implement, right? Because there's too many jumps. So there are ways you can go around this using a jump table. So we're gonna go doing this after the break. So let's do a 10 minutes break. We'll come back at 1:05, right? Let me stop the pause the recording so that we don't have this awkward break in the middle. Okay, so let's implement this in assembly. So the technique called indirect jump involves 2 steps. The first step is to set it up before you actually start to do these jumps. In this case, there are 3 inputs, x and y and c. So let's assume that x is in RDI, y is in RSI, c is in RDX, and you return into RAX. All right. Quick note that W is not initialized in the table because W is initialized in the first line. Okay. The setup has to do with whatever line is coming before the switch case. So here is what I can do. If I look at all the cases here, by what point I know that it's always going to default? When x is greater than 6, right? If x is greater than 6, it's always jump to default because there's no case that's bigger than 6 here. So one thing I can do is to check for x is in RDI. Check for x, I first compare 6 to RDI. RDI is x, right? I compare 6 to RDI. If it's above, right? Jump above means that if it's above 6, you go to L8. By this point, you can probably assume the default is in L8. If it's greater than 6, you go to L8. Otherwise, if it's lower than 6, you always jump to this location. You see parenthesis means what? Address. You jump to some address, right? But in this case, the address you're using, you're pointing to some code that you're supposed to jump to, all right? So now let's break this down. This thing is what? Star.L4. Star.L4 means that the label L4 has some address, right? Star L4 means that I want that address. Whatever that address is, I'm by this point, I don't know, I'm writing assembly. It will have some address, treat that as an address. There's nothing in the base. Then you have, oops, sorry. Then you have %RGI and 8, right? So here, this guy is my D, this is RB, this is RI, and this is S, right? And then your address is basically D plus RB plus RI multiplied by 8. RB is what? It's not defined here, so RB is 0. D is your .L4. It's the location of whatever that label is, right? It's wherever that label is. We're gonna go into that in a bit. Just imagine for now. If X is 0, where do you jump to? Again, here, Ri, this is X. So if X is 0, you jump to what? L4. If X is 1, you jump to L4 plus 1 multiplied by 8, which is L4 plus 8. If X is 2, you jump to L4 plus 2 multiplied by 8. So it's L4 plus 16. So if X, so for this line, right? If X is 0, you jump to L4. If X is 1, you jump to L4 plus 8. If X is 2, you jump to L4 plus 16. Basically, you jump to L4 plus n multiplied by 8. N is the value of X. In this case, it's like 8 multiplied by X, my bad. It's L4 plus 8 multiplied by X. You see why you have to multiply everything by 8 in a bit, all right? But this look like a table that you jump to first. You jump to first. The reason why we have the star here, has the meaning. .L4 alone will go to that location. Star means I dereference the location. So L4 will look like a table. L4 will look like a table. So here is what we call jump table. In assembly, I will define L4. The dot quad means that every line here will take 8 bytes, 8 bytes, 8 bytes, 8 bytes, 8 bytes, 8 bytes, 8 bytes. Inside that line, I will store the first line. I will store location of L8. The second line, I will store the location of L3. Third line, location of L5, location of L9, location of L8, location of L7, and location of L7. Basically means if X is 0, I go look at L4. If I look at L4, what do I see? This is L4. This is L4 plus 8. This is L4 plus 16. This is L4 plus 24. L4 plus 32. L4 plus 40. And then L4 plus 48. So if I look at L4, if I look there, I see .L8. If you remember, indirect jump has star at the beginning. This is jump to star.L8. You dereference and you see, okay, that's the address. You basically now jump to L8. you jump to L8. So if x is equal to 0, you jump to L8. If x is equal to 1, you basically look at L4 plus 8, which means that you jump to L3. If x is 2, you look at L4 plus 16, which means you jump to L5. So depending on the value of x, you jump to different locations. L4 is just a table that tells you where do I jump to, depending on the value of x. All right. Any questions so far? Any questions so far? All right. How many people are confused? Okay. So at L4, you can think of it this way. This is my memory. This is my memory. It starts at L4. Right? You first jump there to that location. Depending on the value of x, and if I break it down, let's say each row here is 8 bytes long. Let's say each row is 8 bytes long, because I specify in my assembly code .quad means that whatever goes there is going to be 8 bytes long. The first row will have .L8. The second row has .L3. The second row has .L5, .L9, .L8, .L7. The last row also is .L7. With me so far. If I go to L3, I will see this table. The first entry is L8, second entry is L3, third entry is L5, so on and so forth. Each entry is going to be 8 bytes long. This is 8 bytes long. This is how wide the whole label .L8 is. Okay? All right, with me so far? Yes.
All the L's,
it represents the code that I label it with, which means that it actually is an address of where that line is.
So why are the first line over?
Why you mean why is it not L1, L2, L3, L4, right? It just when you compile, it just happened to be that way. It's depending on like what come at first, right? And it just happened your switch case might jump to a different location. That's why it's different order. But here, your indirect jump, this is the command. Indirect jump is jump star.L4 with some address that has to do with x, right? RDI is x. So you go L4 plus x multiplied by 8. So if x is 0, you go to the first row. If x is 0, basically you go there, first row. You see L8. If x is 1, you go to the second row, you see L3. If x is 2, you see L5, right? Any question so far? Now you see the label. It can be L8, it can be L3, it can be L5, right? Where are you actually jumping to next has to do with this star. Star means that whatever I see there, I go there. So star means I jump one more step. Basically, I first go to L4. Whatever row I see, I jump to that location. So in this case, let's say x is 0. Ultimately, at the end of the day, you jump to L8. You first go to L4. You see, okay, L8 is here. That's where I want to jump to. Let's say x is 2. Let's say x is 2. So you go to, if x is 2, you're going to see L5, right? The third row, right? You go there. You see, oh, okay, L5. I'm going to jump here. So basically, your code at the end of the day, jump to L5 if x is 2. If x is 6, the last row, if x is 6, you go to L7. You first jump to L4 to see where do you have to jump to next. And the star in front of this jump L4, blah, 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 is just to tell you, you go there first to jump to actually find where you're actually supposed to jump. Yes. Yes. Because if you go look at your switch case, you will, if you remember from the sample, case 5 and 6 happen to do the same thing. So that's why it goes to L7, but they actually do the same thing. Yeah. All right. Any question? Is it more clear now? Yeah. So in general, so now we're going to talk about general case before we go back to that example. All right. Basically, the indirect jump technique use what we call the jump table. That L4, that big table, we call them the jump table. Each row in that table is going to basically become the target of your jump. Now your input, which is X, the input to your switch case tell you what row here that you're going to. Then once you're there, each entry in the row tells you where to actually jump to. This allows you to actually have one compact table that allows you to jump everywhere in your code with one command, which is the indirect jump. Some quick fun thing that I want to tell you now. This is one of the technique that used by computer. For example, when you turn on the machine for the first time, it would have this table that say, if this happens, go to this function call. If this happens, go to this function call. If this happens, go to this function call. They use jump table. In the beginning, this allows you to kind of quickly know what function call you have to run when you're booting up the OS, and start to basically start the boot process and start to run your machine. Now, let's look at jump table again, right? Go back to your switch case, you see that X of 0 is the default case, so that's why you go to L8. Then if X is 1, you go here, right? L3, basically this becomes L3, this becomes L5, this is L9, this is L7, this is L8, the default. And you see that the table corresponds exactly to those blocks of switch case. Okay? All right. If you are with me so far, the next step is to, now we have the setup code that do the indirect jump, right? This is basically, hey, let's jump to the correct location. All right, I'm going to move to the next set of slides that show you how does a jump table look in reality. All right. So now let's say that's your assembly. Okay, with me so please stay with me so far. That's your switch case. I'll go back one slide. This is your switch case function. Go back one more slide. That giant assembly code you saw was this guy plus this guy in the beginning, right? There are two things, the setup code plus the switch case. So here, this is the setup. How can I tell? This is my indirect jump. How can I tell? See the star in front. The star 0x4007F0, and then in parentheses RDI multiplied by 8. That's jump L4 x multiplied by 8. So where's L4? What location is my table? Where's my table here? Where's my table to be located? If I happen to look at this address, right, at this address, so let me actually turn off the light so it's easier to see, right? So the first line of my code, I do that W equals, I didn't do W equal 1, I moved something, and then I compare 6 with X, RDI is XX. And if X is greater than 6, you jump above, jump is greater than 6 to 400614. The address of 400614 is here, right? Again, with me so far. That's just the third line of code. If X is greater than 6, you go to default. My switch case, if X is greater than 6, always go to default for sure, right? it also happened to be the line 400,614, so you can tell that this is the default case. All right, with me so far, we take care of the default that x is greater than 6. Now we deal with the jump table. The jump table, the next instruction say, hey, I want to look at the address 4007FO plus some multiplier of x plus some multiplier of x. That's my jump table. So if I go look at that address 4007FO, 4007F0, you will see my jump table. So one thing I can do is I can print this command, basically will print the content of 4007F0. The /HXQ basically means that I want to print 8 set of data. Each one of them is 64 bits, 8 bytes, 8 pieces of 8 bytes data, starting from 7F0. The first thing you see, 400614, this is again when x equals 0. This is my first row in the jump table. Remember the jump table that has like x is 0 go here, x1 go here, x2 go here. That's the table. If x is 0, go to where? 400614. The next line you run is going to be at 400614. If x is going to equal to 1, then the next line you run is 4005F0. If x equal to 2, you go to 4005F8. If x is going to be 3, if x is 3, you go to 602. If x is 4, 4 is also a default case, so you go to 614. If x is 5 and 6, you go to 60B. All right. Any questions? Are you following me? Okay. So that's the table, but in the actual address. So if you go back, for example, let's go to 5F0 in my code here. This is the code you do if x is equal to 1. Because if x is 1, you go to 5F0. So you do move RSI to RAX and you multiply. Then you return. The next case is 5F8, right? 5F8 is you do this if x is equal to 2. This is a little bit more complicated because you have to follow through. So you do case 2 and then followed by case 3. That's why it doesn't have the return right away. Then you have case 3, my bad. You go to 602, so that's right here. This is when x is equal to 3. If it's 4, you go to 614. If it's 5 or 6. If it's 5 or 6, you go to 60B, which is that line, and you return. All right. So that's why your jump table will, in this case, correspond to this code right here. It just tells you where you jump back to make sure it's correct switch case, right? So now, if you zoom in a little bit here in the case 1, so I just want to extract the code for case 1 here. You see that I do RSI into RX, so you start to assign the return value to be Y, then you multiply with C. You multiply Y with C and return. Again, the return value, we assume that it has to be in RAX, so this will allow you to do that and you can return. In the case of 2, this is a little bit unique in the sense that if it's 2, you first do Y divided by C. In that case, the value of W will change, right? if x is 3, the first line of my code before you go into the switch case, you see that w is going to be equal to 1. But if x is 2, w is not 1 anymore. It depends on y and z. But if x is 3, w is 1. So in this case, your assembly, if x is 2, will first do this, skip this, go directly to this. If x is 3, you will first do this line, then you go here. All right. It will follow this logic, because if x is 3, w is going to equal to 1. But if x is 2, w is not 1. It's y over z. So if you look at the code here, the same code that you saw in the other table earlier, if x is 2, this is the division. So you do y over c, then you jump to this line, which is y over c, then you add w equals to w plus c. All right. So that's when x is 2. If x is 3, you first do w equal 1 here, followed by w equal to w plus c. Now, this is much simpler. If x is 5 or 6, go to L7. L7 is what? You start w equal 1, w equal w minus c, and return. And that's it. All right, and that's it. L8 is the default case, so you assign 2. Here, default w equals 2. All right. So here's the technique for switches, right? So when you have a large switch statement that dense, basically when I said dense means that I want to do check the value of something, and the value for each cases are packed. Can be a 0, 1, 2, 3, 4, 5, 6, 7. If anything more than 7, do this by default. Use indirect jump. What you see so far is jump table. But if your switch cases are sparse, for example, you do switch X, and then case 1, case 1,000, 10,000, for example, and then default. If you have to do a jump table for this, how big is your table? You have to cover 1, you have to cover 10,000. It's going to be a huge table with a bunch of defaults in them. Because if it's 2 default, 3 default, 4 default, the only case you're not default is 1 and 10,000. So in this case, just use nested if else. So the compiler would check your switch case and see if it's dense. If it's dense, use jump table. If it's sparse, where you have the case of 1, 10, 100, in that case, it will not use the jump table because it's a waste of space. It becomes like a bunch of jump, one after another. Just compare jump, compare jump, compare jump. All right. So we actually, this is where I plan to stop today, to be honest. So we have 30 minutes. We can do 2 things. Going over homework if you want. And that was in class from last week. And finish that. I think we should do that, or we can continue on and talk about function call. Basically, this week we'll wrap up x86. Next week we'll start to learn more about how the computer works. All right. So let me motivate this a little bit before we kind of say, okay, we're done with today's lecture. And we do Q&A on homeworks and in-class exercise. Quick thing, your program has function call. All right. Assembly also means that you have to support function call. These are when you have function call, basically what you have to do is you have to establish some rule that say the input will be in what register, for example, right? Let's say you have 5 inputs. How do I find those 5 inputs? It basically means that how does each function communicate and say that's your input is there and that's your return value. And let's say you have nested function call, like Fibonacci or factorial, we have like recursive function, right? The thing is, let's say you call the function. How do you know where to come back? Because your function, for example, you have this function y equal function q, right? You call function q. When you finish function q, basically this allows you to go down here. Then you finish function q. Then you need to remember, hey, go back to that line and not the beginning of function p. How do you do that? Who's responsible for saving? That was my program counter of the line that you have to go next when I finish my function call, right? This doesn't sound too complicated when you have only one function call, but let's say you have recursive function. Another, like I call this function call the same function over and over and over again. How do I know where I am? And how do I know where is the line do I go back to? All right, so on Thursday, we will talk about the discipline around the assumption that we have to make sure that we can have a functioning program that can handle function call. All right, we will talk about passing the data in, how to assume where is my return value. Quick hint, return value is always in RAX. It's just every single program when you write and compile, you will assume that your return value is going to be in RAX by default. How do I manage the memory when I have another function call that do malloc? What if I have a function call that do int I, right? Because I don't know how many times this function is going to get called, so I cannot just simply say allocate one integer. If the function gets called 3 times together in a recursive fashion, means that I need 3 versions of I, right? For the first function that call the next function, that call the next function. How do I keep it possible that you can finish the innermost function and go back to the outer function? And how do we deallocate this in I when we finish the function call? All right, so that's going to be on Thursday. For now, the lecture basically is over. I don't want to start function call yet because it actually can take. Yeah, actually, that's the thing about open house because I did not know that. Do we have class during open house?
No, they're class. It's online.
Oh, I can do online. Oh, actually, let me check. So, quick question: If how many people would prefer online? I mean, I for sure do. I don't want to drive here 30 minutes each way, but
Yeah, the other class online switched over.
okay. So let me double check with the policy quickly with OAA and see if we can do online because I mean I think it's a prep for open house, which means you guys like some of you guys might be like helping out with like the like building the booths and everything. I'm not sure how it works. To be honest, yeah, that's a good point. Let me check quickly and I'll make an announcement. If it's online, I'll just basically use the same WebEx link. All right. If it's offline, I'll be here. How many people have to help out with open house task? No. All right, good. That's like awesome. So worst come to worst, I'll be here and I'll go over a function call. All right. It's just a matter of like where is the class gonna be. For the earlier class of PCSA, I basically told the students that I will do a review because they have exam on Friday. So it's kind of perfect timing for them. So this I'll first check with OA and see if we can do online. How many people have like the other classes online as well on Thursday? How many people have no class on Thursday? You have no class Thursday. All right. If I can do online, one thing I can probably do is like do the review we have so far with like data representation, assembly, and going over because I'm about to launch assignment 4, which has to do with the bit manipulation, and that's like an auto grading script. So by the time you submit, you know what score you're gonna get. I'll let you know how to use it. I'll maybe go to like a 2 questions there. That's the simplest one. Like the default, you need to get this kind of thing anyway, so that you know how to write the code and how to set it up and to test it. All right, if that works. So does it work better for you guys that way? Okay, then we'll cover like assignment 4 and review. Then we'll resume function call on next Tuesday because we definitely have enough slot for everything. All right, cool. All right, so let me stop the recording now. And we do in class. If you want,